You're studying for your board exam and time is running out. Fortunately, it's pass-fail, but still, how should you spend your time to maximize your chance of passing? That is, with 1 week to go before the exam, what factors will make you more likely to pass than to fail? Will things like the number of hours you study, or how many nights you sleep at least 8 hours, or the number of days you exercise affect your odds of passing? This, you realize, is a question you can approach using logistic regression. Regression describes the relationship between an outcome and individual predictor variables. When the outcome of interest is continuous, say your numerical score on the exam, you use linear regression. When the outcome is binary, say you either pass or fail, you can use logistic regression. You can use simple logistic regression with just one predictor variable, or multivariable logistic regression with many predictor variables. Let's work through an example. Imagine you're designing a study to evaluate the radiographic features of lung nodules that may predict lung cancer. You start with a model that predicts the likelihood of cancer based on the nodule size. You review CT scans from thousands of patients who were found to have lung nodules and who underwent biopsies, noting how large each nodule was and whether each nodule was found to be lung cancer. And you record some other variables too. Because you only have two possible outcomes, cancer or no cancer, it of course doesn't make sense to draw a line of best fit to model these data, as you would with linear regression. Instead, you use logistic regression to model the probability that a lung nodule of a certain size represents lung cancer. While the outcome, cancer or no cancer, is binary, the probability of cancer or no cancer is continuous, ranging from 0 to 1. The logarithm of the probability of one outcome over the other, or the log odds, is used to transform this probability into a range that includes any value. Logistic regression models a linear relationship between the predictors and the log odds of the outcome. Each coefficient of a predictor in your logistic regression equation tells you how the log odds of the outcome changes with a 1-unit change in that variable. Here you see that for each 1 millimeter increase in size, the log odds that the nodule is cancer increases by a fixed amount. The coefficients tell you how the log odds of the outcome changes with a 1-unit change in that variable, holding the other variables constant. You can exponentiate these coefficients to get odds ratios. For example, a 1 millimeter increase in nodule diameter here would imply an odds of cancer about 3 times as high. You might want to express the result in terms of probabilities. If you feed the logistic regression output into a sigmoid function, which is actually the inverse of the log odds, it can squeeze the output back into a range between 0 and 1 to describe a probability. And for that, it matters where you start. For a very large lung nodule that has a very high probability of being cancer, each additional 1 millimeter increase in size doesn't change that probability by much. But for values in the middle, a 1 millimeter change in size likely changes that probability by much more. Let's discuss a few key assumptions underlying logistic regression. First, the relationship between the inputs and the log odds of the output has to be linear. If the data takes some other shape, this model won't work. Second, you assume a lack of strongly influential outliers in the dataset. If removing a single patient from the sample strongly changes the prediction, it could be a clue that something unusual or not accounted for in the model is going on with that patient. Third, you assume the absence of multicollinearity, meaning the independent variables in the model should not be highly correlated with each other. For example, it may not be a good idea to have separate variables for both the size of the nodule, measured as length in the largest dimension, and the estimated volume of the nodule. While not the same, it's quite likely that those two measures are tightly linked. Fourth, logistic regression assumes independence of errors, which means that error terms, or residuals in your statistical model, are not correlated with each other. One note of caution: it's very important to characterize the population in which you are applying your model. In other words, consider the generalizability. A model developed for lung nodules in patients who presented to a thoracic surgery clinic may not be appropriate to apply to all comers, say in a primary care clinic, because the risk profile for the patient population used to create the model likely differs from that for all comers. Back to your impending board exam. You survey your colleagues who recently took the test, and after analyzing the results, it seems pretty clear. At this stage, those late-night cramming sessions don't seem to be associated with much benefit. But sleeping well and exercise do. That settles it. Time to prioritize sleep and exercise leading up to test day. Let's go.